Integral 23. Let's compute this integral. Integral from 0 to infinity cosine x to the 2n over x squared plus 1 dx. N is larger than 0 and integer. Firstly, we rewrite cosine x using exponential functions. We substitute e to the ix plus e to the minus ix over 2 into the integrand and expand the parentheses. Here we define the function fz equal 1 over z squared plus 1, sum k equals 0 to the n minus 1, 2n choose k e to the I 2k minus 2nz, plus 2n choose n, over 2. This corresponds to half of the full sum. Next, we evaluate the contour integral along the path on the right. There is a simple pole at 0 equal I minus I, and we should note that the contour is oriented clockwise. Therefore, the integral is given by minus 2 pi times residue z equal minus I. The integral along the path C1 is given as follows. For the integral along C3, we must make the substitution z equal minus z dash. Then we change the summation index by letting j equal to n minus k. Using properties of binomial coefficients, we shift the range of summation from n plus 1 to 2n. By adding the integral along C1 and C3, we obtain 4 to the n times the desired integral. Finally, we evaluate the integral along C2 and show that it vanishes. The reason we take the contour in the lower half plane is precisely to ensure that this integral converges to 0. We parameterize the contour by z equal re to the I theta, where theta is 0 to minus pi, and denote this integral by j. We estimate j from above. Using the fact that absolute value of a sum is bounded by the sum of absolute values, we evaluate each term separately. Since e to the I alpha has magnitude 1, the expression simplifies accordingly. For sufficiently large R, the exponential term e to the minus 2k minus 2n r sin theta tends to 0 for k is less than n, because the exponent goes to negative infinity. Thus, the integral converges to 0. Moreover, the term without the exponential also vanishes, since the denominator has higher degree. Therefore, the contribution from C2 is 0. Combining all results, we obtain the final expression. So, the final result is here. Thank you.